Picture this. You're a detective stepping into a chaotic room. You have to make a huge decision, but you definitely don't have all the facts. Absolute certainty? Yeah, that's completely out the window. So what do? Well, you do exactly what we humans do every single day. You look at the clues, you weigh the evidence, and you make your best call based on probability. And it turns out, machine learning can do exactly the same thing. Welcome to the Explainer. Now, if you've been hanging around the machine learning world, you might be super used to algorithms like support vector machines. You know, the ones that use rigid geometry to draw strict boundaries between data points? Well, today, we are leaving those geometric boundaries entirely in the rearview mirror. Instead, we're diving into a purely probability-based algorithm called Naïve Bayes. Trust me, it is one of the fastest, simplest, and literally most widely used classification algorithms out there. Here's our roadmap for demystifying this incredibly powerful baseline algorithm. We'll kick things off with the power of probability, then move into updating beliefs with Bayes. Next up is the naive independence assumption, step-by-step predictions, 3 naive Bayes variants, and finally, we'll wrap it all up with real-world applications and limits. Section 1. The power of probability. Before we even touch the algorithm itself, we really have to recognize that humans naturally estimate likelihoods all the time. Think about looking out your window in the morning. If you see dark clouds, crazy wind, and it's super humid, nobody can guarantee it's going to rain. But you naturally estimate the probability, say an 80% chance, and you just grab an umbrella. You made a decision without certainty. Notice how machine learning handles this in 2 completely different ways. A support vector machine looks at a data point and asks, okay, which side of the geometric boundary does this belong to? But Naïve Bayes asks something totally different. Given the evidence, which class has the highest probability? It's exactly like a doctor looking at a patient with a fever and a cough. The doctor doesn't draw a line on a graph. They calculate whether it's more probable that the patient has a common cold or pneumonia, and they go with the highest probability. Section 2. Updating beliefs with Bayes. So, how do these probabilities actually change when fresh clues pop up? This brings us to the actual mathematical engine of our algorithm, invented over 250 years ago by an English mathematician and minister named Thomas Bayes. The whole trick is understanding how Bayes' theorem works at its core. It always starts with a prior probability. This is just your initial belief before you see any new evidence. Say a hospital knows that only 2% of adults have a certain rare disease. That 2% is the prior. But then, a patient takes a blood test and it comes back positive. Boom, that test is your new evidence. Bayes' theorem takes the prior, multiplies it by the likelihood of that new evidence, and spits out the posterior probability. The posterior is just a fancy way of asking, okay, what do we believe now after seeing this new clue? You literally do this in everyday life without even thinking about it. You wake up, clear sky. You figure there's a 10% chance of rain. That's your prior. 10 minutes later, dark clouds roll in. You don't completely restart your brain. You just update your thinking. Your belief scales up to a 40% chance. 30 minutes later, thunder and wind hit. Your estimate updates again to 90%. That continuous real-time updating of beliefs based on new independent clues, that is exactly how Naïve Bayes arrives at its final posterior probability. Section 3. The naive independence assumption. So why call it naive? I mean, it almost sounds like an insult, right? Well, it gets that name because it makes a massive assumption. It assumes every single input feature is completely independent of the others once the class is known. True independence is like rolling 2 dice. The first die has absolutely zero effect on the second. But we know the real world is messy and connected. Fever and cough aren't truly independent. They usually show up together. But Naïve Bayes takes a major shortcut. It says, look, let's just assume these symptoms act completely independently, only once we know the patient actually has influenza. We call this conditional independence. By ignoring all those complex correlations, like how temperature and humidity interact in a wildfire, the heavy math becomes incredibly fast and super easy for a computer to process. Section 4. Step-by-step predictions. Now that we have the theory down, let's open up the algorithmic black box. How exactly does Naïve Bayes transform raw clues into a final classification? Let's use an email spam filter as our example. Here is the exact step-by-step prediction workflow. Step 1. Calculate the prior. Out of all your emails, how many are usually spam? Step 2. Measure the likelihood of the features. In this case, the actual words in the email. Step 3. Combine those using Bayes' theorem. Step 4. Compute the final posterior probability for both spam and not spam. And step 5. Simply select the class with the highest probability. Now, here is a really cool detail. When you have dozens of features, multiplying tiny probability decimals makes the numbers so incredibly small that computers actually lose numerical precision. They just can't handle it. So modern libraries like scikit-learn automatically use logarithms. They add log probabilities together instead of multiplying them, which keeps the math perfectly stable behind the scenes. Let's see how this builds a rock-solid case. If an email hits your inbox with the words free, winner, and prize, the algorithm checks the historical probability of each word. The word free appears 70% of the time in spam, but only 5% of the time in regular emails. Naïve Bayes essentially multiplies the probabilities of all these clues together. Just like that detective we talked about earlier, piecing together fingerprints and a broken window, these multiple independent clues overwhelmingly increase the confidence that the email is, without a doubt, spam. Section 5. 3 Naïve Bayes variants. Now, you can't just use one single version of this algorithm for every problem. Think about it like a mechanic. You wouldn't use a hammer to tighten a screw. A data scientist has to pick the correct version of Naïve Bayes for their specific data type. If your data is continuous, like temperature or blood pressure that follows a natural bell curve, you'd use Gaussian Naïve Bayes. If you're counting things, like how many times the word winner pops up in a text, you use multinomial Naïve Bayes. And if your data acts like a light switch, purely binary, true or false, like whether a patient has a cough or not, you go with Bernoulli Naïve Bayes. Honestly, choosing the right variant is often way more important than any crazy fine-tuning you could possibly do. Section 6. Real-world applications and limits. So, how does this model actually hold up out in the wild? Well, despite its totally unrealistic, naive assumption, this algorithm is an absolute powerhouse. It trains incredibly fast. We're talking sometimes just seconds. It handles text classification so brilliantly that it's the backbone of countless modern spam filters and sentiment analysis tools. Plus, it naturally gives you percentage probabilities, which makes explaining the results super easy. And for the developers out there, it requires almost no feature scaling and practically zero hyperparameter tuning. It just works amazingly well right out of the box as a lightweight baseline model. But how do we really know it's working? We can't just look at basic accuracy. We have to dig deeper using a confusion matrix, like this one used for predicting wildfire PM 2.5 risk. This table breaks down our true positives, true negatives, and false negatives. From this, we can calculate precision, which is how often our warnings are actually right, and recall, which is how many real risks we successfully caught. Then we use F1 scores to balance the two. This shows us exactly where the model succeeded and where it completely missed the mark, giving us a much more complete picture of its performance on complex environmental data. So, where does Naïve Bayes sit in the grand ecosystem of machine learning? When should you use it over a heavy, complex algorithm like a random forest? Well, if you need incredibly fast, probability-based text classification, and your features are mostly weakly dependent on each other, Naïve Bayes is definitely your go-to. But if you're dealing with a highly complex dataset where the intricate relationships and interactions between features really matter, Naïve Bayes is going to struggle because of that independence assumption. In those heavier cases, a random forest or gradient boosting model is going to serve you better. Ultimately, though, Naïve Bayes is the absolute perfect baseline to start with. So, we've seen how algorithms use geometry, and now we've seen how they use probability based on neat little mathematical rules written by humans. But it begs a massive, completely fascinating question for the future. How do machines learn when they stop following our human-coded math rules entirely and start mimicking the biological structures of the human brain itself? That evolutionary leap takes us straight from algorithms like Naïve Bayes directly into the wild realm of artificial neural networks and deep learning. But hey, we'll leave that thought hanging for you to ponder. Thanks so much for joining this explainer, and keep exploring.